So for any system, any quantum system, a microscopic system of energy, it can gain a photon or absorb a photon to gain energy, or emit a photon to lose energy. And that one photon has an amount of energy that's proportional to the frequency or inversely proportional to the wavelength. And that photon is just acting as the transfer of energy. But the system itself has its own formula for energy, and different types of systems have different formulas. If you're talking about a hydrogen-like atom, like a small atom with only one electron, the usual formula for that is proportional to Z squared, it turns out, where Z is the atomic number, and inversely proportional to some other whole number squared. It turns out that for most quantum system, most atomic systems, like the size of an atom or smaller, what we mean by quantum or quantized is that the energy doesn't really have infinite variability. You can have this much energy, or this much energy, or this much energy, but the in-between values don't work. So n in this case represents some whole number. And there's also another constant multiplier here that turns out to be a negative 13.6 electron volts. So the negative 13.6 electron volts is just a constant to get the units to work out right, electron volts being a unit of energy. Z is the atomic number. So for instance, 1 for hydrogen, 2 for helium, whatever you look up on the periodic table. And then N is a whole number. So 1, 2, 3, 4, etc. Positive whole number. And what this tells you is certain specific values for energy that are possible for that atom. That atom can have this much energy, or this much energy, or this much energy, but the in-between values do not happen. And ultimately, this is because of the idea of standing waves. One of the core principles of quantum mechanics is that things like an electron or a photon or anything really acts like both a wave and a particle at the same time. That there's not really a distinction between things that are waves and things that are particles, but they're essentially just two different behaviors of the same type of thing. So the electron has momentum in the sense that it's moving like a particle, but the electron also has a wavelength as if it were a wave. And likewise, a photon has a wavelength because it's a wave, light is a wave, but it also has momentum as if it were a particle. So if we treat the electron as a wave that's confined to a certain region of space, like let's say you've got a narrow region of space, or in this case, the entire atom, and the electron can only exist in that region of space. If you've got a wave that is confined to a certain region of space, what sort of behavior does that become? A wave in a confined space, just bouncing back and forth. What sort of interference pattern would you expect there?
We would get like a standing wave.
Yeah, so, sorry, go ahead.
I was going to say we would get a standing wave.
Yeah. And so if you've got something like an electron confined to a finite region of space, like if it's trapped in the atom itself, it's just orbiting the nucleus. If you treat the electron as a wave, it has to be a standing wave because it's in this confined region of space. So if we go back to the idea of standing waves on a guitar string, for instance, only certain values of wavelength will work. You can't have just any wavelength. If you have like a guitar string or an enclosed pipe, we'd expect the endpoints would have to be nodes. And you could have this wave as a standing wave, so nodes on the ends and an antinode in the middle. Or you could have also a node in the middle. So you could have something like this. So the wavelength could be half that much. Or we could have maybe two nodes in between. So you could have a standing wave that looks like this. Or you could have more nodes in between. But each one of these standing waves has a certain wavelength. So certain wavelengths will work, but the in-between values won't work. You can't just have any value for wavelength because most wavelengths will not form a standing wave on this region of space. Only certain permitted wavelengths will work. And each one of those wavelengths ends up having a certain amount of energy associated with it as well. The hydrogen-like atom, the math ends up being a lot more complicated, but you still end up with the electron is in a confined region of space. So only certain wavelengths will work as standing waves. And that translates to only certain energies will work. So the hydrogen-like atom can only have certain specific values of energy, which are described by this equation. And the in-between values do not happen because they wouldn't form standing waves. Any questions on that so far? Then let's try out a quick example. Let's say we're specifically talking about hydrogen itself. For hydrogen, what is the atomic number?
One.
Yeah, very beginning of the periodic table. One proton, so Z equals 1. So if we write out the energy formula, we get E equals negative 13.6 electron volts, just a constant to make the units work out right, times 1 divided by n squared, where n, once again, can be any whole number, usually called the quantum number of the system. For that reason, we often write this as E sub n, in the sense that energy depends on the value of n. So you'd have energy level 1, energy level 2, energy level 3, and so on. And we can calculate some of those if we fill in various values for n. And I often find it useful to sketch these out on a graph of energy. I mean, kind of a graph. It's really more of a number line. The way we usually draw this, let me take this up a little bit. The way we usually draw the energy levels as a diagram is by drawing a vertical line that represents all the possible values of energy. So let's say this vertical line is various different values of energy. If we start filling in some n values, we can fill out possible locations on this energy axis. For instance, what would be the lowest n could get here?
N equals 1.
Yeah, so if we fill in 1 for n, we could say E1 is negative 13.6 divided by n squared. So 1 squared, that'll just be negative 13.6. And the units will be electron volts. Electron volts, EV, being a tiny quantity of energy. Specifically, it means the charge of an electron times 1 volt. That works out to some tiny number of joules, but we can just use electron volts as our energy unit here. And what would be the next energy we could have if we fill in n equals 2? What would you get for E2 here if you fill in 2 for n?
Negative 13.6 divided by 4.
Yeah, which I think is negative 3.4. So that would be the next energy higher, because negative 3.4 is greater than negative 13.6. In fact, it looks like as we fill in a larger n value, this is going to get to a higher number, because dividing by a larger number leads to a smaller fraction, but it's negative. So as n increases, we're getting closer and closer to what's this going to approach as n gets larger and larger? What's the highest this could possibly get?
It's 0.
Yeah, if you fill in an extremely large number for n, you get negative 13.6 divided by something really, really big. That's going to be almost 0. So 0 is the limit here. As we increase n higher and higher, the energy values get closer and closer to 0, but never quite reach it. So if we map these out, and I usually just draw these as horizontal bars on this energy axis, the lowest we would have is negative 13.6. So negative 13.6, that's the n equals 1 case. That's the lowest energy this system could have. And then the next one above that would be 3/4 of the way to 0, up to negative 3.4. So negative 3.4, this is the next value of energy the system could have. Or what if we fill in n equals 3? Negative 13.6 divided by 3 squared, what's that going to be?
It's like negative 1.5.
Yeah, about negative 1.5. So that'll be the n equals 3 case, the third harmonic. Because this is really acting very much like standing waves. We get these specific harmonics, and the in-between values do not work because they don't form standing waves. So negative 1.5, that's a little more than halfway up from there, something like that. What about for n equals 4? If you fill in 4 for n, so divide by 16, what would you get?
3.95 or 85.
Okay.
I think it's 85.
Dividing by 16, yeah, about 0.85. So negative 0.85. And the divisions here are getting smaller and smaller, these separations between energy levels. Because we're going from negative 1.5, a little less than halfway up. So something like this. And I'm not going to fill in these specific numbers for the other ones because it's going to get too crowded. But these do end up being banded closer and closer together. So we get these energy levels very close together and getting closer and closer to 0, never quite reaching it. You're going to have infinitely many different energy levels packed in together here, but they get closer and closer and closer. And of course, physically, you can add enough energy to bring it above 0, but it turns out that when you bring it above 0, you're adding enough energy to break the electron out of the atom. You are breaking the bond, much in the same way as the Lennard-Jones potential energy stuff from way back in 7A. So if you start at negative 13.6 and add 13.6 or more, you're adding enough energy to break the electron out of the atom. But let's say you're at negative 13.6. What's the only way you could go up energy here? If you're at negative 13.6 to your starting point, like, could you add 5 electron volts? Would that work? Can you go from negative 13.6 up to negative 8.6 and stop there?
You can't, because the energy levels are discrete, so you have to add enough to get to the certain energy level that you want.
Exactly. You can only jump up or fall down to another permitted energy level. So if you add exactly enough to go from negative 13.6 up to negative 3.4, in other words, what, 10.2? That would be a permitted delta energy. So it's possible for this atom to, if it starts off at the lowest possible energy level, what we usually call the ground state, it's possible for it to gain plus 10.2 electron volts. Or alternatively, if it absorbs enough energy, it might jump up to a higher energy level. Maybe it gains 10.2 and ends up at n equals 2. Or alternatively, maybe it gains enough to jump up to the n equals 3 state. It could gain from negative 13.6 up to negative 1.5. That's plus 12.1. So delta energy could be plus 12.1 electron volts. That's also a possibility. If it gains exactly that much energy, then it'll jump up to another permitted energy level. The energy of this equation is really describing the energy of the whole atom, including the electron. If I remember correctly, I think it's a combination of both the potential energy of the electron's interaction with the nucleus and also the electron's kinetic energy as it is in motion. But you can think of this as just lumping together the whole energy of the entire atom. So when you add energy, we usually describe it as bringing the electron to a more excited state in terms of it now has more energy. But any of these changes are possible as long as you start and end at permitted energy states. So these are some examples. In this case, from negative 13.6 to negative 0.85, that'd be plus 12.75. So that's another possible change in energy. So these are three of the possible amounts of energy the atom could gain if it starts off in its lowest possible energy state. But how does it gain that energy? What provides energy to an atom? Yeah, if you shine light on the atom, specifically if a single photon of light hits the atom, then the atom gains the energy of that photon. So we could set each of these delta energies equal to energy of one photon, going back to this conservation of energy idea. The delta energy of the system, which in this case is the hydrogen-like atom, equals plus or minus energy of the photon that's associated with that change. In this case, we're gaining energy, so we're assuming we're absorbing a photon with that much energy. So what we could do then is set each of these changes equal to energy of one photon. And this will allow us to figure out what photons this atom could absorb. So the atom could, if it's in its ground state, it could absorb a photon that has exactly 10.2 electron volts of energy, or the same ground state atom could absorb a photon with exactly 12.1 electron volts, or with exactly 12.75 electron volts, or some other values depending on what these higher energy states are. But if you know the energy of one photon, what else can you calculate about that photon? What determines how much energy a photon should have? Yeah, the frequency, or sometimes more usefully, the wavelength. And usually we describe light in terms of its wavelength. So in this case, let's use the hc over lambda version. What we can do is then we can set each of these amounts of energy, the energy of one photon, equal to hc over lambda, and then solve for lambda. So if energy of one photon equals h times c over wavelength, how would you isolate wavelength in that formula?
Would you divide by HC on both sides?
The problem is that would leave us with 1 over lambda. So what else would we need to do?
And then take the inverse of that?
Yeah, so that should work. Instead of E over hc, we get hc over E. So h times c divided by energy of one photon. So we can use that to figure out the possible wavelengths that will work. H times c, and we could look up Planck's constant and speed of light and multiply them, or h times c is often just used as a constant in its own right. Anyone happen to know what that constant is? It should be in electron volts times nanometers as the units.
Is it like 6 point something? Oh, wait.
This one actually works out to a pretty reasonable number because Planck's constant is extremely small, speed of light is extremely large. So h times c, the very small and very large kind of balance out. I think is it 1200 or 2400? Double check that. Constants. Go look this up. That's just the 1240, I think, 1240. So Planck's constant times speed of light is 1240 electron volt nanometers. Where again, electron volt is a tiny unit of energy, which is often used when dealing with very, very small systems. And nanometers is just a distance, very small distance, which we often use for measuring the wavelength of light, since that tends to be around the order of a few hundred nanometers. So if we fill that in, 1240 electron volt nanometers, and divide that HC by each of these possible photon energies, that will give us several possible wavelengths for the light. So we get, for instance, 12.75 as the E photon. If we take 1240 as HC and divide by 12.75, so 1240 electron volt nanometers divided by 12.75 electron volts. What happens to the units of measurement there?
The electron volts cancel.
Yeah, so we just get nanometers, which is usually the units we want for wavelength of light. And that works out to about 97. So about 97.23-ish nanometers. So that means if the wavelength of the photon, if the wavelength of the light is exactly 97.3 nanometers, then that means a photon of that light has exactly the right amount of energy to jump the atom from the ground state up to the n=4 state, which we would sometimes call the third excited state. You got ground state, first excited state, second excited state. Third excited state would be n=4. Or we could just say the fourth energy level. So if the photon, if the light being shown on the atoms has exactly this wavelength, then the energy per photon will be exactly the right amount to get absorbed by the atom, jumping it up to the fourth energy level. Or alternatively, if the photon has 12.1 electron volts, we could use the same equation, HC over E photon. So H times C, again, 1240 electron volt nanometers, divided by this energy, 12.1 electron volts per photon. And I'm getting about 102.5. So that's another possible wavelength that the light could have. If the light has either one of these wavelengths, then the photon would get absorbed by the atom that it hits. Or for this other one, 10.2 electron volts. We could again type in 1240 divided by that other frequency, the other energy, 10.2. So I'm getting about 121.6 nanometers. So any of these three wavelengths of light will have photons that can be absorbed by this atom. And there are others as well, because you could go from ground state up to fifth energy level, ground state up to sixth energy level, and so on. But all of those will require photons with slightly more energy, which means slightly lower wavelength. So these will be the longest wavelengths of light that could be absorbed. And I'm noticing these are all fairly short wavelengths. Visible light is, I forget the exact values, but somewhere between like 200 and 800 nanometers. So these wavelengths of light will not even be visible light. There will be too short wavelength, that is too high a frequency to be seen. So visible light won't work here. You need higher frequency, shorter wavelength, maybe ultraviolet or beyond. But those wavelengths, if the light has any of those wavelengths, it'll be absorbed. If it has in between values, like let's say the light has a wavelength of 110 nanometers, and you got these hydrogen atoms in the lowest energy state, so cold hydrogen gas. and you shine light that has a wavelength of 110 nanometers, what would you expect to happen? If you got this cold hydrogen atom and light heading towards it, that's 110 nanometers wavelength. What would you expect to happen there? Can that atom absorb that light?
Yeah, it would be able to.
Is 110 nanometers one of the wavelengths that has the right amount of energy?
Oh no. So it has to have like that specific wavelength to be absorbed.
Right, because if it had 110 nanometers of wavelength, that means its energy wouldn't be 10.2 or 12.1 or 12.75. It'd be somewhere in between. In other words, if the wavelength was 110 nanometers, the wavelength would, or the energy would be something like this amount, somewhere in between. And you can't start at n equals 1 and end somewhere in between n equals 2 and n equals 3. You can only, the atom can only exist at these specific values of energy. The in-between values do not work, again, because it wouldn't form standing waves in the correct space. So in a photon that doesn't have exactly one of these wavelengths, if it's somewhere in between, that wavelength, that photon will not get absorbed by the atom. The atom cannot accept that amount of energy, only the specific values that lead to the correct ending points. So in that case, if the wavelength does not have one of these permitted amounts of wavelength, the photon is just going to go right through. It doesn't get absorbed. It doesn't interact with the atom at all, which means that the light, the hydrogen gas would be transparent to that wavelength of light. Any wavelength that doesn't get absorbed just goes through. So this is ultimately why certain chemical or certain elements are transparent to some wavelengths of light, some colors, or some categories of light, but block other categories of light. So if you just shine light of lots of different wavelengths, just white light mixed to lots of different colors, these wavelengths will get blocked, but the other wavelengths will pass through. And so you can use this to analyze gases. If you've got some mixture of gases and you don't know what elements are in it, you can shine light on it and figure out what wavelengths get through versus what wavelengths get blocked. If you've got a gas that blocks these three specific wavelengths, 121.6 nanometers, 102.5 nanometers, 97.3 nanometers, but allows other wavelengths through, you can be pretty confident that that gas is hydrogen because of the behavior of what energies get through and what energies don't. Any questions on that so far? And of course, that's assuming that we are starting at the ground state. It's possible that we start at different energy levels. Like maybe we started at, maybe we start at the n equals 2 level. If you start at n equals 2, where could you go from there? If we call this initial. You could, for instance, absorb a photon and gain enough energy to jump up to what? Can you go just like partway?
To like anything higher than n equals 2. It's like n equals 3 or 4.
Right. Maybe you gain exactly enough energy to jump from n equals 2 to n equals 3. And note that that's going to be a smaller amount of energy than going from n equals 1 all the way up to n equals 3. This allows a different type of photon to be absorbed. Or yeah, maybe from 2 to 4, or maybe from 2 to 5. So you could calculate each of those delta energies, treat that as the energy of the photon that's being absorbed, and then convert that to a wavelength using, once again, hc over energy. So that would tell you the wavelengths of light that the slightly higher energy atom could absorb. And it is possible to have this happen in multiple steps. Maybe the ground state atom absorbs a photon that bumps it up to the n equals 2 state. And then maybe it very shortly thereafter absorbs another photon that happens to be exactly enough to bump it up to n equals 3. So you can do this in multiple steps as long as each step starts and ends at permitted energy levels. Alternatively, if it's n equals 2, instead of going up, it now has room to go down. It could drop all the way to n equals 1, in which case it would be losing energy. In this case, if it drops to n equals 1, delta energy would be negative, 10.2? Yeah. It could be losing 10.2 electron volts. And how does the atom lose energy? Where does that energy go? How does the energy leave the system?
It emits a photon.
Yeah. If the system is losing energy, it does so by a photon leaving the system. So the atom spits out a photon. Let's say the photon is emitted here. A single photon of light leaves the system, and that photon of light is carrying the energy that the system has lost. So in this context, we would say delta energy of the system, instead of saying it equals the energy of the photon, we'd say it equals the opposite of the energy of the photon. Or to put it another way, we could say energy of the photon is absolute value of energy of the system, or change in energy of the system. Yeah, let me clarify that. Energy of the photon is generally going to be absolute value of change in energy of the system. So we could say energy of the photon is positive 10.2 electron volts, leaving the system. And if we solve that for energy for the wavelength, we're still going to get 121.6 because we're still using the same value for energy. So if the atom is in the n equals 2 state, it could drop down to the n equals 1 state by emitting a photon with this wavelength. So this would be the emission of the photon. It could spit out a photon with exactly that wavelength, that color. Or alternatively, let's say you started in the n equals 3 state. If you start in n equals 3, you've got a couple of different ways you could lose energy. You could emit a photon that drops you from energy 3 to energy 2, or from energy 3 all the way down to energy 1. So that means if you're in the n equals 3 case, there are 2 different wavelengths of photons you could emit, 2 different colors of light that atom could glow with. And this is also why a hot object can glow. If it's very hot, that means the atoms are at a high energy state. As they decay to lower energy states, they emit that energy as a photon. If the photon has a wavelength that's in the visible range, you're going to see that object glow because it's so hot. That's the energy leaving the system as light. Even if it's not visible light, the energy is still leaving the system as light. It's just in a wavelength that we wouldn't be able to see. Any other questions on this idea of energy levels and photon emission and photon absorption?
Could we also lose energy if we were to like form a bond with the hydrogen?
If you're forming bonds, does that work?
Because like, I guess if you like form a bond and you like combine the 2 energy diagrams, like the position of the energy levels have to kind of change.
Yeah, if you're forming a bond, that's a loss in energy, right? Yeah, forming a bond means the bond energy is decreasing. So that means the energy has to go somewhere. So yeah, I think you could interpret that as the energy leaving the system in the form of a photon. I'm not sure what that would be in terms of formulas, but in general, each system, each type of energy at the atomic level involves different formulas. So for instance, this negative 13.6 electron volts times z squared over n squared, that only applies to the energy of the whole atom, specifically an atom with 1 electron. So different systems will have different formulas for energy of the system. But the idea of energy of the photon that transmits the energy, that's universal. A photon's energy will always be hc over wavelength. or h times frequency, whichever one you're looking for. And the energy of the photon will always be absolute value of the change in energy of the system. But the energy of the system could use different formulas depending on what type of system it is. I guess the 7a analogy would be that energy of the system might be potential energy or kinetic energy or thermal energy or bond energy, whatever type of energy is changing. But work and heat are always going to be what contributes energy to the system or takes energy away from the system. The quantum version of that is there are different kinds of energy, different kinds of quantum systems that could be changing. But in all those cases, the photon is what's transmitting the energy, what's carrying energy to the system or carrying energy away from the system. And the photon is always going to have hc over lambda as its energy. Any other questions on that?
No, thank you.
You're welcome.
Oh, I had one more question.
Yeah, go
ahead. You said if like the atom absorbed enough, like a big enough photon to reach zero, it would just break the atom?
Yeah, for instance, let's say you have an atom that starts off in the ground state and you hit it with a photon that gives it, let's say, 14 electron volts of energy. At that point, you've brought the energy above zero. So it doesn't really even matter if there's a permitted energy state there or not. You've now added enough energy that the electron can leave the system, which means it no longer has to form a standing wave. So it doesn't have restrictions on what its energy can be. And ultimately what happens there is when you add, let's say 14 electron volts, the first 13.6 electron volts go into breaking the bond. The extra leftover energy, the extra 0.4 electron volts, will become the new kinetic energy of the electron. So the more energy you add all in one go, not only do you break the bond, but also you make the electron leave pretty quickly with a lot of kinetic energy. That's also the basic concept of how solar panels work. You want a material where sunlight hitting it gives the atom enough energy that the electron can leave and have enough extra energy to form electrical current as it moves around.
I was just gonna say, was a 14, was that a number that, like, as an example, or you calculated that?
Which 14? Oh, just the energy being added? That was just one possible example. As long as you're adding enough energy to overcome the gap from zero up, from the lowest energy up to zero.
Okay.
So that amount of energy, and I think that's usually called the work function. The work function of the atom is how much energy it would take to just barely break the bond and separate the electron. Anything above and beyond that much energy, the work function, is the extra energy that the electron now has for kinetic energy. So at that point, and again, at that point, you've now broken the electron out of the atom. So the idea of only discrete energy levels doesn't really apply anymore. That's only when it is bonded and you have this standing wave situation. And again, other systems will use different formulas for energy. This energy for the hydrogen-like atom, that's just for the hydrogen-like atom. If you've got something like an electron in a box, sort of situation, an electron in a confined space, that's going to have a different equation. Or if you have a quantum oscillator, like two atoms vibrating against each other, that's also going to have its own different equation for energy of the system. But it still follows the same pattern of only certain specific values will work, and you gain or lose energy by absorbing or emitting a photon that has that amount of energy transfer. So try that out with some examples. Let me know if you have any questions, and I will see you next time.
Thank you.
You're welcome.